Dear students, welcome to the lecture series on the topic engineering graphics. So today we are going to discuss about the applications of the auxiliary planes in engineering graphics. I am Dr. AIP Ahuja, Professor, Department of Mechanical Engineering, Punjabi University, Patiala. So the two views of an object, that is front view and the top view, which are projected on the principal planes, vertical plane and horizontal plane respectively, are sometimes not sufficient to convey all the information regarding the object. So this thing usually happens when the components whose projections are to be obtained on the principal reference planes, they are containing certain surfaces which happen to be inclined to both the reference planes. So whenever these inclined surfaces are projected onto horizontal plane or the vertical plane, it happens that the projections of these surfaces, they appear to be smaller than the actual shape and size of the inclined surfaces. So we work out that the front view and the top views which are projected corresponding to these inclined surfaces on VP and HP, they do not describe the actual shape of these inclined surfaces. So the additional views which are called the auxiliary views are therefore required to be projected on other planes which are known as auxiliary planes. So the auxiliary views, they are used in engineering graphics for determining the true length of an oblique line and also determine the auxiliary views of an oblique line. Other applications of the auxiliary views, they include evaluating the point view of a line, evaluating the edge view of a plane, evaluating the shortest distance between point and a line, then working out the shortest distance between skew lines, and the skew lines are the lines which are neither parallel to each other and they are not intersecting with each other. Similarly, other applications of the auxiliary views, they are obtaining the true size and form of the oblique plane. So whenever we have the oblique planes, once again, since they are both inclined to HP and VP, so the front view as well as the top view which are projected again on the principal planes VP and HP respectively, they will not be able to provide us with the true shape and the true size of the oblique planes. So we are going to require once again auxiliary planes or the auxiliary views to demonstrate working out of the true shape and the size of the oblique plane. Similarly, the auxiliary views, they are required to evaluate the true shapes of the cut sections of the solids as well. So we can see that we had used the rotation of the line method to evaluate the true length of the oblique line. So the rotation of the line method had only one application, whereas the auxiliary views, we can see that they have multiple applications in the engineering drawing. So here we can use the auxiliary planes or the auxiliary views to solve different varieties of the problems in engineering graphics. Now, first of all, we need to develop an understanding about what is an auxiliary plane. So any plane which is perpendicular to a given reference plane and it is inclined to other reference plane, it is called an auxiliary plane. So basically it is an imaginary plane which is drawn parallel to the surface of the component or the object which is inclined to either HP or VP, so that we can derive or we can obtain the true shape of the inclined surface which is inclined to either HP or the vertical plane. So the view of an object which is obtained on an auxiliary plane, it is called auxiliary view. And in engineering drawing practice, there are two auxiliary planes which are usually used, and the names of these auxiliary planes, they are auxiliary inclined plane, which we are going to refer to as AIP, and auxiliary vertical plane, which is usually referred to as AVP. So these two planes, they will be used to derive the true shapes of the surfaces of the objects which happen to be inclined to the horizontal plane and which happen to be inclined to the vertical plane respectively. So let us first of all define the auxiliary inclined plane. So an auxiliary inclined plane, again it is an imaginary plane which is drawn with respect to the horizontal plane, and this AIP will always be inclined to the horizontal plane and this will be perpendicular to the vertical plane. So this is usually used, this AIP is usually used to evaluate the true shapes of the surfaces which lie on any given object or the component which happen to be inclined to the horizontal plane. Similarly, AVP, that is the auxiliary vertical plane, it represents a plane which is inclined to the vertical plane and it is perpendicular to the horizontal plane. So AVP will be used to obtain the true shape of those surfaces which happen to be inclined to the vertical plane. So by using these two planes, what we are going to do, we are going to draw these two AIP and AVP parallel to those surfaces which are inclined to HP or VP respectively, in order to obtain the auxiliary planes getting parallel to these inclined surfaces, and in a way they are going to provide us the true shapes of these inclined surfaces. So the AIP and AVP, they are seen as straight lines or the edge views in front view and top view respectively. So this we are going to see shortly, how AIP and AVP, they will appear as straight line or the edge view in front view and the top view respectively. And these lines, that is AIP line and AVP lines, they are called auxiliary reference line. Just like you see, we have already known by now that XY line is our reference line. So XY line is going to separate horizontal plane from the vertical plane. Similarly, we are going to draw projections across these AIP and AVP reference lines, and AIP reference line will be drawn inclined to HP and AVP reference line will be drawn inclined with respect to the vertical plane. And these lines will be denoted by these notations, that is x1 y1 and x2 y2. So whichever, whether AIP or AVP, whichever reference line or the auxiliary plane we draw, first of all the numbering for that will be written down as x1 y1. Whichever auxiliary plane we are drawing second, so the numbering for that will be going by x2 y2. And auxiliary planes, whenever they intersect with the reference planes, they will provide us with the horizontal trace and the vertical trace of these planes. So let us see, how do we represent an auxiliary inclined plane? So as we have already discussed, AIP represents a plane which is inclined to HP and it is perpendicular to VP. So this is the spatial representation of the auxiliary inclined plane, and we have already said that this plane is inclined to the horizontal plane and this is vertical, this is perpendicular to the vertical plane. Now you can see that since this is a plane which is inclined to horizontal plane, so we are going to draw this AIP parallel to the inclined surface of the component, and once this plane gets parallel to that inclined surface, so the true shape of that inclined surface will be appearing on this particular AIP, and whatever view will be obtained on AIP, this will be called auxiliary plane. And if we extend this AIP, you see, because this is inclined to the horizontal plane, if I extend this AIP, so once it intersects with the horizontal plane, so this location is going to describe the horizontal trace of my AIP. Similarly, if I extend my AIP towards the vertical plane. So wherever the extension of this AIP intersects with the vertical plane, we are going to obtain the vertical trace of this particular AIP. So you can see the vertical trace is inclined at an angle theta, whereas the horizontal trace will appear as vertical line below the XY line. So the projections which are obtained on AIP, I have already explained, they will be called as auxiliary plan. And you can see, if we are looking from the front, this is our complete AIP, and looking from the front, this AIP will start appearing like a straight line. So we are going to get the edge view of this AIP as we are going to look on the vertical plane from the front view. So the AIP will appear as a straight line or the edge view when we are looking from the front in the front view. Now let us see the orientation, because I have already told you, depending upon the inclination of the surface, I have to rotate this AIP, and this angle theta will be varying depending upon the orientation of one of the surfaces which happen to be inclined to HP. So depending upon the angle of inclination of the surface of the component, the angle of inclination of the AIP will also be changing. So this angle theta may vary along this 180-degree coordinate location. So we'll see that in the next slide. So here you can see once again, so the AIP is represented as an inclined plane. As you look from the front view, it will appear as a single straight line. So we call that single straight line as the edge view of the auxiliary inclined plane. So this is inclined at an angle theta with respect to the horizontal plane, and this AIP will be perpendicular to our vertical plane, and depending upon the orientation of the surface, this angle theta will be varying. And you can see over here we have represented, you can have the angles theta 1, theta 2, theta 3. So it can be along this orientation or it can be along this orientation. So in either case, you are going to set this AIP in accordance with the orientation of the surface whose true shape is to be obtained, and accordingly you can see horizontal trace will stay in its position, and depending upon the changing orientation, the vertical trace of the AIP may change depending upon the angle of inclination of this AIP with respect to the horizontal plane. So let us work out how we draw the auxiliary vertical plane. So AVP we have already defined as it is a plane which is inclined to the vertical plane and perpendicular to the horizontal plane. And since this plane is inclined to the vertical plane, so the true inclination of this plane with respect to vertical plane, the angle of inclination is called angle phi. The orientation of AIP with respect to HP was called theta, whereas the orientation of AVP with respect to the vertical plane, this angle is called angle phi. So you can see once again, this is our auxiliary vertical plane, and what for this will be used? This AVP will be used to derive the true shape of the inclined surfaces of the objects whose surfaces they happen to be inclined to our vertical plane. So once again, just like AIP, the angle phi can vary, and this angle phi can vary along the 180-degree coordinate location with respect to vertical plane. AIP angles, they were drawn with respect to HP. AVP angles, they are drawn with respect to the vertical plane. So you can have AVP in this orientation, you can have AVP in this orientation as well. And if we extend our AVP, you can see if I extend it vertically downwards, so the intersection, if I project it downwards onto the horizontal plane, the intersection of the extended portion of this AVP with respect to HP will provide me the horizontal trace of this AVP. Similarly, if we extend this AVP towards the vertical plane, then the intersection of this AVP with respect to VP will provide us with the vertical trace of the plane. So vertical trace, you can see it is vertically upwards with respect to XY line, and the top view will show us the horizontal trace which will be inclined at an angle phi, and the view which will be obtained on the AVP, this is called auxiliary elevation. Why this is called auxiliary elevation? Because the dimension, the distances from the XY line of the projection lines from the elevation, they are drawn onto the AVP. So that is why the view which is projected or which is obtained on AVP will be called auxiliary elevation. And let us see the again spatial orientation one more time. So this is how we represent our AVP. So AVP will be inclined with respect to VP at an angle of phi. So phi is the true angle of inclination of AVP with respect to the vertical plane, and it will be perpendicular to the horizontal plane. Now here you see the angles of orientation of this vertical plane. With AVP with respect to the vertical plane can vary, so angle phi can vary. So you can have AVP in this orientation, or you can have AVP in this orientation as well. So here the vertical trace will remain same, whereas the horizontal traces, they are going to vary depending upon this orientation, because the angle phi 1, phi 2 and phi 3, they are going to change depending upon the measure of the angles phi 1, phi 2 and phi 3. So let us now, having understood the locations of AIP and AVP, let us work out the importance of auxiliary planes or auxiliary views in the engineering graphics. As I have already explained to you, there will be many of the surfaces on the components which are going to be inclined to either HP or they are going to be inclined to VP. So here we have component number 1. We can have a look at this component. So once we have this as this component over there located in first quadrant, and we are going to look at this component from the front side. This is our front view. If we are looking at this component from the front view, the true shape of the surface number 3 will be obtained. Why? Because this surface number 3 happens to be parallel to the vertical plane. So the true shapes we have indicated by circle. So this is the surface number 3. If anything is displayed in circle, it means it is going to represent the true shape of that surface. Similarly, this was my front view, and I was getting the edge view of this surface. Now this is the inclined surface in which I am interested, where the auxiliary views will be required. Why this will be required, we are going to work out in a while. So please see, this is our front view. In the front view, for this inclined surface, I am able to obtain the edge view only. Please see, the edge view of the surface is obtained in the front view, which is my slanted surface. Similarly, if I look at this surface from the top, now the true shape of the surface 2 will be obtained. Why? Because surface 2 happens to be parallel to horizontal plane. So I am again marked surface 2 in circle. But the problem lies here, because if I am looking from the top, this is an inclined surface which is inclined to HP. If the surface A happens to be inclined to HP, its projection on horizontal plane will be appearing to me as an apparent shape. So apparent shape will be smaller than the true shape of this particular surface. So this surface is not represented appropriately on the horizontal plane. Let us work out the side view. If I am looking at this component from this side, left hand side, my view will be obtained on the right hand side, and view will be obtained on the profile plane. And if I am looking from this side, you can see surface 1 happens to be parallel to the profile plane. So the true shape of the surface 1 is obtained on the profile plane, and I have marked this in circle once again. But problem lies here as well regarding surface A, because surface A is not represented appropriately on the profile plane, because it is also inclined to the profile plane. So since surface A happens to be inclined to the profile plane, so its projection on the profile plane will appear to be shorter one or reduced one, and that is why we call the surface as apparent shape. So if we draw all these 3 views over here, this is front view, this is my top view, this is my side view, left side view. So again, for surface A, side view shows the apparent view, top view shows the apparent view, front view shows the edge view. Now what I have to do, wherever I have obtained the edge view of the surface, I am going to draw my auxiliary inclined plane, which will be inclined to HP and perpendicular to VP. So this AIP I am going to draw parallel to the edge view of this surface, whose true shape is to be obtained. And once I draw my auxiliary inclined plane parallel to this surface, so now this surface and this inclined plane AIP, they are parallel to each other. And once I draw the projectors over here, I will work out that this true shape of the surface could be obtained onto this inclined plane. So this is how I can obtain the true shape of an inclined surface using an auxiliary inclined plane view over here. So this view will be called auxiliary view. Similarly, you can see over here, if I am drawing an auxiliary plane parallel to this, since this plane is parallel to this surface, its true shape will be appearing over here. Again, I have marked the surface in circle with capital A. So this is true shape, this is true shape, and this is again true shape of the inclined surface. So this is the first application of the auxiliary view that we need to understand. Now the second one is, please check this out. If again a similar one, same example in the different orientation. If we are looking from the front, again the edge view we have been able to obtain. This is the surface whose true shape is to be determined. So I have used edge view, I have used the top view. Again in top view, the apparent shape of the surface is available. Here the edge view of this surface has been obtained, and wherever the edge view is available, you can see I am using the auxiliary inclined plane over here. And once I use the auxiliary inclined plane and I draw the projections over here, now you can check the true shape of this surface, which is much bigger than this apparent shape. This will be obtained. So that is how the auxiliary planes and auxiliary views are important in engineering graphics, because they facilitate you to evaluate the true shapes of those surfaces which happen to be inclined to either the horizontal plane or the vertical plane. So this is the true shape of this particular surface which has been obtained over here. Similarly, I'll show you another example where if we do not use the auxiliary planes or the auxiliary views, even the distortion in the dimensions will be possible. So here you can see, here we have one component, a similar one, again having an inclined surface, but this surface is having a circular hole. Please check, this surface is having a circular hole. But if I look at this surface, this object from the front, let us say this is my front view. If I'm looking at this surface from the front, this circle will start appearing to me like an ellipse which has been reduced from the height side, and this appears as an ellipse which is located horizontally basically. So if I start manufacturing this component, I am not going to get my desired component appropriately. So this shape is getting distorted. So ellipse is oriented horizontally. Similarly, if I look at this object from the top, so this circular hole which was lying on the inclined surface, it will start appearing to be again as an ellipse, but this will be there now in the vertical orientation. So this is horizontal orientation, this is vertical orientation. So again, not only the orientations are changing, but the shape of the circle starts appearing to be an ellipse over there. So let us explain this once again with the help of a proper figure. So you can see this is the component which is having an inclined surface, and this inclined surface is having two circular holes. If I am looking at the surface from this side, so these two holes, which should be the circular ones, they start appearing to be like an ellipse which is oriented horizontally. So they do not describe the actual shape of this. Not only that the size of this particular rectangular component is getting reduced, but the shapes are also started getting distorted over here. Similarly, I am looking at this component now from the top. If I am looking at this component from the top, these two circular holes, now they start appearing like ellipses, but now in the vertical orientation. So this is ellipse which is located in vertical orientation. Again, these two ellipses, they are shown in horizontal orientation. So I do not get the complete description of the shape and size and the form of the object. So the manufacturing will not be possible based upon these drawings. So what I need to have, I need to have an additional plane. So HP and VP, they are not sufficient to give me the exact details of these components. So what I am going to do, in whichever plane I am going to get the edge view, I will be drawing that particular view over here, draw the projection lines, and now draw an AIP which will be parallel to this inclined surface. So once I draw an AIP or AVP parallel to this surface, so this surface projection on the AIP or the AVP will provide me the true shape of this section. Now you can see the circular holes, they are being reflected, they are being drawn appropriately, they are being represented appropriately onto my true shape view. But this is not possible in the front view or the top view or even in the side view. So that is why the auxiliary planes will be required to describe the appropriate size and shapes and forms of those objects, those surfaces of the objects which are inclined to either horizontal plane or the vertical plane. So this is my true shape. Just see, this is my true shape of this particular surface A over here. Similarly, another example, here you have again an inclined plane. If you are looking from the front, this surface will appear to be very short. You cannot make out whether it is an inclined surface over here. So though you can see it's a very long surface. Similarly, from the top, because it is inclined surface, because of the inclination, shape is little bit shortened one. But in the side view, you are able to obtain left side view, which is drawn on right hand side. You are able to obtain the edge view of this particular surface. So you need to obtain the edge view of this surface, inclined surface. And once we are able to obtain the edge view of the surface, once again the projector lines we are going to draw from here, and we'll be able to get the true shape of the surface onto the AIP or the AVP, whichever way, whether the inclination is there with respect to HP or whether the inclination is there with respect to vertical plane. Now we are going to discuss the applications of the auxiliary planes. The first application of the auxiliary plane method is to evaluate the true length of an oblique line. We have already learned how to determine the true length of an oblique line using rotation of the line method, and we will see how the auxiliary plane method compares with rotation of the line method towards evaluation of the true length of an oblique line. So to begin with, we are going to draw the projections of an oblique line, and then we will see how we can move forward evaluating the true length of the line using the auxiliary plane method. So the end A of the line AB is 10 millimeter in front of VP. So you see, we have drawn the projection of the top view of the end A 10 millimeter below the XY reference line. The distance between the end projectors of ends A and B, they are 50 millimeter apart, and the top view of the end B lies 50 millimeter in front of VP. So the end B we have drawn 50 millimeter below the XY line. Similarly, you can draw the front view elevation A dash B dash, and now we need to join A with B. Now let us draw the projections of the line in the front view. Now end A of the line lies for 40 millimeter above the horizontal plane. So we have drawn end A dash 40 millimeter above the XY reference line. Similarly, end B, the information available with us, it is 10 millimeter above the horizontal plane. So end B we have drawn, that is point B dash, we have drawn 10 millimeter above the XY reference line. Now we can join A dash, B dash and ends AB. So A dash, B dash, it is the front view elevation of the oblique line. AB, it is the top view or the plan of the line AB. Now earlier on, what we were doing in the rotation of the line method, we were rotating the projection in the front view, that is A dash B dash, so as to make it parallel to the XY line, that is parallel to the horizontal plane. And once this front view projector A dash B1 dash, it was parallel to the horizontal plane on the horizontal plane, that is in the top view. So between these coordinate locations of A and B, we used to obtain the true length of the line. So here we used to require to draw long locus lines from all these endpoints A dash, B dash, A and B. But in this case, in the auxiliary plane method, what we are going to do, that rather than rotating the line A dash, B dash to make it parallel to the horizontal plane, we are going to draw an imaginary auxiliary inclined plane parallel to this elevation projection line A dash B dash, so that we need not rotate this line. So now the plane we have drawn, AIP, we have drawn parallel to the elevation projection line A dash B dash. Now whatever projections we are going to obtain on this AIP, those projections will provide us the true length of the line in plan. So here you see, I am going to draw these two projector lines, and these projector lines, as we already know that projector lines must be perpendicular to the plane of the projection. So the first projector line and the second projector line, which are drawn through A dash and B dash points, so they will be perpendicular to the X1 Y1 auxiliary inclined plane. Now having drawn these projector lines, we already know that whenever we used to rotate this line, make it parallel to the horizontal plane. Now on the horizontal plane between these two coordinates, 10 millimeter and 50 millimeter. So between these two coordinates we used to obtain the true length of the line. Now we have made a plane parallel to the projection line rather than making line parallel to the projection plane. So it is the same thing. Now what I am going to do, I am going to mark these two distances. What are these two distances? Distance of end A in plan from the XY reference line, you see it was same case over here, and distance of end B from the XY reference line, again we can check, this distance was distance of the end B from the XY projection line. So between these two projectors we used to obtain the true length of the line. So same thing we are going to carry out over here, that is the distance of the plan, because in the horizontal plane, in the top view, I am going to obtain the true length of a line. Now I'll mark this distance, I'll measure this distance first of all, 10 millimeter. And what is this distance of 10 millimeter? It is 10 millimeter in front of VP. Front of VP means it is a positive distance. Now from this X1 Y1 reference line AIP, I am going to mark 10 millimeter ahead of this particular plane. So I'll measure this 10 millimeter, mark it in front of the plane because this distance was there in front of the plane. Mark this 10 millimeter because I am marking the plan point. So name of this point will be A1. Similarly, I'll measure this distance as 50 millimeter. Distance of the end B from the XY reference line. It is same as distance of the end B from the XY reference line. So I'll measure this distance from this plane. Mind you, you don't have to measure distances from A dash and B dash. You are required to measure the distances from X1, Y1. Now this distance of point B from the XY line means that this is a distance of the end B in front of VP. Front of VP means positive distance. So again, I am going to mark this distance in front of the plane, 50 millimeter. So having obtained these 2 points A1 and B1, I am able to obtain the true length of this particular line. This line will be A1, B1 will be the true length, since A dash, B dash, that is the elevation projection line, happens to be parallel to the AIP reference plane X1, Y1. And having obtained the true length, now I can evaluate the angle of inclination of the top view of this true length with respect to the vertical plane, and name of this angle is angle phi. and this angle we used to work out as angle phi over here. So this angle we are going to measure, and the true length of the line we are going to measure. And as we have already discussed, that any projections which are obtained on the auxiliary inclined plane, they will be termed as auxiliary plan, because the distances of the plan have been marked onto the projection lines which are drawn on the AIP. Now let us draw the second auxiliary plane, which is called AVP. Now AVP is drawn, please remember, AVP is drawn parallel to the plan projection line, and AIP is always drawn parallel to the elevation projection line. Another thing, you have to keep minimum distance, that is around 1 centimeter, between this elevation projection line and the auxiliary plane. Similarly over here, we have to keep minimum distance between this plan projection line and the auxiliary vertical plane that we have drawn. So since this plane has been drawn in the second iteration, so the numbering for this auxiliary vertical plane reference line will be x2, y2. Had we drawn this AVP first, then this numbering would have been x1, y1, and obviously we would have drawn this in the second iteration. So the numbering 1 would have been replaced by number 2. So this would have become x2, y2. This would have become a2, b2. So since we have drawn these first, so the numbering will be a1, b1, x1 and y1. So now since we are drawing this auxiliary vertical plane in the second iteration, so the numbering will be followed for the reference line as x2, y2. Now once again, I need to draw the projection lines through A and B points, which will be perpendicular to my auxiliary vertical plane. And let us see how we are going to draw it. You see, two projector lines I have drawn, and these projector lines, they will be perpendicular to the plane of the projection. Now let us see what happened in the rotation of the line method. In the rotation of the line, this was the plan projection line. We used to rotate it to make it parallel to the vertical plane, and once we made it parallel to the vertical plane, then we were drawing the projection or the extension of this projection over here onto the vertical plane, so as to obtain the true length of the line on the vertical plane in the front view. That is a dash, b2 dash we used to obtain as the true length. And between which coordinates this was obtained? Once again, coordinate distance of a dash from xy, coordinate distance of end b dash from xy. So these two distances were used, and these were the projector lines which were used to establish the true length of the line AB. Similarly, now over here we need not rotate the line, so we have drawn a plane parallel to the existing plan projection line. So since my plan projection line happens to be parallel to the AVP, now on AVP means it is parallel to my vertical plane, and now on the vertical plane in the front view I am going to get my true length of the line. So I need to measure the distances in the front view. Please see, this is the distance of end A in the elevation, 40 millimeter. I'll measure this distance, and what is this distance? This is 40 mm above the horizontal plane. That is, again, it is a positive distance. So end A of the line lies 40 mm in front of the above the horizontal plane. So here again you can check. This is my new plane AVP, which is x2 y2. I have to draw the same distance positive. Positive means above the plane, so above the horizontal plane. So I have to draw this distance in front of the plane or above the plane, 40 millimeter. Similarly, over here, what is the location of the coordinate B dash in the front view? This is 10 millimeter above. That is once again positive. So I'll measure this 10 millimeter from the plane x2 y2. So I'll measure this distance 10 millimeter positive, that is above my horizontal plane. So name of this point is A2 dash, because the value 2 comes because this is the second iteration. I am measuring the A dash distance. So obviously the name of this point is A2 dash. Here again you can see we were getting the true length in the front view, that is A dash B2 dash. So here this is A2 dash and this point is B2 dash. And now we are going to join A2 dash with B2 dash, and having joined this, we have obtained the true length of the line. And if this true length of the line A2 B2 dash is equal to the true length of the line which was obtained in the plan, that is A1 B1, then we can conclude that our procedure has been implemented in the optimum way, that is the methodology has been applied correctly. So both the true lengths need to be equal, because a line cannot have two different true lengths over there. And having evaluated the true length, because this is the true length in the elevation, so whatever is the angle of inclination of the true length in the elevation, that angle name is called angle theta. So the angle theta is angle of inclination of the true length of the line in the elevation. So with the XY line or with my horizontal plane. So this angle also I can measure. So just like method of rotation of line, I have been able to evaluate both the true lengths and angles theta and phi using the auxiliary plane method. So we can see that this is a method which is a shortcut for evaluating the true length of an oblique line. And again, you can check both the true lengths, they have been worked out to be equal, and the projection which is obtained on the auxiliary vertical plane will be called auxiliary elevation. Why auxiliary elevation? Because the distances of the front view have been used to obtain this particular true length. So the view which will be obtained on the AVP will be called auxiliary elevation. View which is obtained on AIP will be called auxiliary plan. So this is the first case regarding evaluation of the true length of an oblique line when the ends A and end B, both of these ends, they are lying in the first quadrant. Now we are going to pick up another problem just like in the previous tutorial, that what happens when we are required to evaluate the true length of an oblique line, but the first point of the line happens to lie in quadrant number 1 and the second end of the line lies in quadrant number 3. So let us first of all draw the projections of the line. So end A of the line is lying 10 millimeter in front of VP. Distance between the end projectors is 50 millimeter, and end B of the line, it lies 40 millimeter below the horizontal plane and 25 millimeter behind the vertical plane. So you see first end A, it lies 35 mm above HP and 10 mm in front of VP. It means it lies in the first quadrant. So see 35 mm above HP, we'll get A dash, 10 mm below XY line, we are going to get end A. Distance between the end projectors is 50 millimeter. End B lies 40 millimeter below the horizontal plane and 25 millimeter behind the vertical plane. It means it lies in the quadrant number 3. So B dash point will be drawn below the XY 40 millimeter and end B will lie 25 mm above the XY line. Now very carefully, we need to join A with B and A dash with B dash. A common mistake which again many students make, they join these two ends over here. No, in this case the first point lies in quadrant number 1, so elevation will lie above XY, plan will lie below the XY line, and the second point B, it lies in the third quadrant, so the front view will lie below the XY line and the top view will be lying above the XY line. So A dash and B dash we need to join. So this is my elevation projection line. Similarly, A and B, that is plan projection line, I need to join. Now in the earlier case I told you that any auxiliary plane which is drawn parallel to A dash B dash will be AIP and it should be drawn quite close to the line. I can over here also draw an AIP very close to this, but what will happen when I draw the projections on the AIP, all these values, all these whatever constructions I am going to make, they are going to interfere with each other. Why? Because my two ends, they are lying in the different quadrants, and A is lying in first quadrant and B is lying in the third quadrant. So in this case, the distance between A dash, B dash and AIP, and similarly the distance between AB and the AVP should be drawn in such a way that they are at a reasonably large distance. Large distance does not mean that you should draw it very far away. Large distance is that AIP should be drawn parallel to A dash, B dash, but it should be drawn clear of this image. Whatever data is given, clear of that data, I need to draw my AIP. Just see, I have drawn x1, y1. So this is my first auxiliary plane. I have named it x1, y1. Since I have drawn this auxiliary plane parallel to A dash, B dash, the name of this plane is once again AIP. Now through A dash and B dash, I will be drawing two projector lines which will be perpendicular to the AIP x1, y1. So just see, I have drawn these perpendiculars over here. Now after drawing these perpendicular projector lines onto x1, y1 through the points A dash and B dash, now I need to draw the auxiliary plan onto my AIP. In order to draw auxiliary plan, I need to mark the distances of the plan for end A and for end B onto this particular x1, y1 reference plane. So please see, how do we do the marking? The marking is with respect to the A dash projector line, I have to mark the coordinate location of the end B and A in the plan. So what is this coordinate location? End A lies 10 millimeter in front. In front means it is positive distance. So ahead of the plane. Front of the plane means ahead of the plane. So end A lies 10 millimeter ahead of the XY reference plane. So I am going to mark my end A1 10 millimeter ahead of the plane. But what about end B? End B lies 25 millimeter behind the vertical plane. This is in front of the vertical plane 10 millimeter, and B lies 25 mm behind the vertical plane. So behind the vertical plane means this is negative. So I cannot draw 25 millimeter again in the positive direction. I have to mark this point B in a negative way, that it will be behind the plane. So this point has to be marked 25 mm behind the x1, y1 vertical plane. So just see, this is 10 millimeter ahead, this is 25 millimeter behind. So once I locate these 2 points A1, B1, that is points of the auxiliary plan, I obtain the true length of this line. So this blue line represents the true length of the oblique line, whose front view was given to me as A dash, B dash. So having obtained this true length, now the angle of inclination of this true length with the AIP, this gives me the angle phi, because this is the true length obtained in the plan. So since this is the auxiliary plan, so you can see that this is a true length. So since this length is auxiliary plan, so plan makes an angle of phi with respect to the reference plane over here. Now next, I want to evaluate the true length of the line in the elevation as well. So for that, what I have to do, I have to draw my AVP, which will be parallel to the plan projection line. So here is my plan projection line AB. So once again, clear of the picture, because this portion has already been used. So clear of the picture, I will draw x2, y2. Why x2, y2? Because this is my second auxiliary plane which I am drawing. So second iteration. So it is parallel to AB. So it is called AVP. Now two projector lines I am going to draw through A and through B. So through ends A and B of the plan projection, I am going to draw two perpendicular projectors. You see, I have marked these perpendicular projectors over here. And now I am going to mark the distances of the elevation. Why? Because any view which is obtained on AVP, it is called auxiliary elevation. Now what are the coordinates of the elevation of the ends A and B? So end A lies 35 millimeter above the horizontal plane. Above the horizontal plane means positive. You see, 35 mm above HP. So end A lies 35 mm above HP. So this is the locus line for the projector A. So from here, I will mark 35 millimeter positive above the plane or ahead of the plane. So just see, this is my point A2 dash. This is my point A2 dash. But what about B2? Now check, A dash point lies 35 mm above XY line, which means it is positive, but and B, that is in the front view, this lies 40 mm below the horizontal plane. It lies 40 mm below the horizontal plane. So below the horizontal plane means negative. So from here I have to go negative behind. This is above, this is behind. So this is 40 mm behind, this is 35 mm in front. So once I obtain both of these 2 points, A2 dash and B2 dash, so I can join both of these points, A2 dash with B2 dash, and this gives me the true length of the line in the elevation, that is in the front view. And having obtained this true length, I need to carry out the matching of this true length with the true length which has already been obtained in the plan, that is A2 dash B2 dash. This distance must be equal to distance A1 B1, and if both of them they are equal, it means all the iterations have been carried out appropriately. So line cannot have two different true lengths. So though both of these true lengths, they should be equal. Difference is, this is the true length in the plan and this is the true length representation in the elevation. And now we can measure the angle of inclination of this true length with the reference plane, and this angle is called angle theta. So we can see that this is the procedure how we can evaluate the true lengths of the line in elevation and the plan, and we can also evaluate the angles of inclination theta and phi with respect to HP and VP. So this was our question number 2. So this is again true length, and let us work out question number 3. So here we do not want to evaluate the true lengths, because true lengths we already know how we can evaluate that. But in many instances there will be oblique lines which the observers they might be viewing from different positions. So we are going to see to it, if the observer is situated at a particular position with respect to AIP or with respect to AVP, how those observers they will be able to visualize the lengths of the oblique line. So first of all, let us draw the projections of the line, and D of the line DE is 10 millimeter in front of VP and 40 mm above HP, that is it lies in the quadrant number 1. Distance between the end projectors is 55 millimeter, and E of the line it lies 5 millimeter above HP and 35 mm in front of VP. So again this line lies in the quadrant number 1, and D also lies in the quadrant number 1. So end D you can check, it lies 40 millimeter above HP and 10 millimeter in front of VP, and E of the line lies 5 millimeter above HP and 35 millimeter in front of VP. Now these are the projections of the oblique line. Now we do not want to evaluate the true length. True length, if we would have required, we would have drawn AIP parallel to this, AVP parallel to this, just in the same way that we have proceeded in the last 2 problems. But here the criteria is that I want to see if my observer is located at an angle of 60 degree to horizontal plane, how much length of this line will be visible to that observer. Now this 60 degree you could have taken it this way, 60 degree you could have taken it this way. So AIP angle 60 degree you could have taken it this way or this way. But if we take 60 degree angle this way, much of the line will be visible over here. If I take 60 degree angle over here, this I'll also be showing, then this line view will be reduced too much. So even though technically this would be correct, but we will like that we should arrange our AIP or AVP with respect to our original lines or original surfaces in such a way that the biggest view should be obtained, largest possible view of the object should be obtained on my AIP or the AVP. So over here I'll just show you, if I draw my AIP 60 degree will be this angle over here, then very large length portion of the length will be visible over here. So since this AIP is not parallel to this projection line, so whatever auxiliary plan view will be obtained over here, this will not be the true length. This will be again apparent length of the line. This is apparent length in elevation. This is apparent length in plan. But what happens if the observer is looking at this line through AIP at an angle of 60 degree? How much length of the line will be visible, will be apparent to the observer? This part we want to know in this particular question. So once again, we have drawn an AIP at the given angle, assuming that the observer is looking at this line from this orientation. So what will happen? Once again, through D dash and E dash, I will be drawing two projector lines which will be perpendicular to the x1 y1 AIP. So just see, through D dash and E dash, I have drawn two projector lines which are perpendicular to the reference plane x1 y1, because all the projectors, they should be perpendicular to the plane of projection. This thing we need to remember. And having drawn these perpendicular projectors through D dash and E dash, now we need to measure the distances from the plan and mark it over here. So distance of ND 10 millimeter in front of VP, distance of E 35 millimeter in front of VP. So 10 is also positive, 35 is also positive. So I will be drawing ahead of the plane, front of the plane 10 millimeter along the D dash projector line through from x1 y1, and similarly I will be drawing 35 millimeter distance from x1 y1 in front of the plane. So both of these distances, they are positive. So points D1 and E1 of the auxiliary plan have been realized, and I will be joining this line. But mind you, this is not a true length. This would have been true length had I drawn AIP parallel to D dash E dash. So since this AIP is not parallel to D dash E dash, so the length which is obtained is again apparent length, which is visible to the viewer or the observer who is observing this line or this projection at an angle of 60 degree from the front view side. Similarly, now I want to write down auxiliary plan. Now similarly, I'll draw AVP. Again, you can draw AVP 45 degree over here, or you could have drawn AVP 45 degree over here. Had I drawn 45 degree AVP over here, the projectors would have given me very short view of this line. So this I'll demonstrate to you in couple of minutes. So here you see, I have drawn an AVP in this orientation at 45 degree, assuming that the observer is looking at this line from this orientation, and bulk of the view will be observed by the observer over here. So the length of the line which will be visible or apparent to the observer will be very large as compared to the position if had the observer been viewing this line from this orientation. So let us see, I have drawn AVP at an angle of 45 degree. Now my plan projection points, they are D and E. Through D and E, I will be drawing perpendicular projectors from D and E onto AVP. And please check that this AVP is not parallel to the plan projection line DE. So I am not going to get the true length of the line over here in the auxiliary elevation. So two projector lines I have drawn which are perpendicular to x2, y2. Now which distances I am going to mark? Since I am going to get auxiliary elevation over here, so the distance of the elevations I am going to plot. So the distance of end D dash in front view is 40 millimeter above the horizontal plane. Above horizontal plane means positive. Distance of ND, this is 5 millimeter above the XY line or the horizontal plane. So this is also positive. So the D distance, you measure it from here, from the projection plane, 40 millimeter above the reference plane, 40 millimeter, mark a point. Similarly, E distance, this is 5 millimeter above the horizontal plane. So both of these points, they have been marked. So the name of these points will be D2 dash and D2 dash. Why D2? Why A2? Because this is the second iteration. Why dash? Because we are measuring the elevation distances over here. So this point is D2 dash, this point is E2 dash. And what is this? This is my, once again, apparent length. This is no longer a true length. And the name of this view which is obtained on AVP, this is the auxiliary elevation, because the distances of the elevation side we have plotted over here. So in this lecture we have talked about the basics of the auxiliary plane. Besides this, the two applications of the auxiliary planes we have discussed, that is how to evaluate true length of the line. So we have also discussed the comparison of the rotation of the line method with the auxiliary plane method. And then the second application of the auxiliary view, that is evaluating the auxiliary views with respect to AIP and AVP. How do we evaluate that? And the remaining applications of the auxiliary views we are going to take up in our subsequent deliberations in the next lectures. So let us see, we have drawn these points over here and very big lengths we have also evaluated, but again, even though they are not the true lengths, but they are apparent lengths which are good enough, which are very showing you the larger information about the projections of the line. And I told you earlier that if we are using the AIP and AVP in the different orientation, shorter lengths would have been visible. So these are the alternate solution, not good one, but it is again technically correct. Had I taken AIP in this orientation, so I have drawn AIP at an angle of 60 degree, then through D dash and D dash, again I am drawing the vertical projector lines perpendicular to x12, x11 and y12, and then I'll mark these distances 10 millimeter and 35 millimeter. Both are front of VP, that is positive. So 10 millimeter I draw here, 35 millimeter I draw here, and this is my auxiliary plan. So just compare this view of the line with this view. So this view is much shorter than this view. That is why we are not inclined to draw this view, even though this is technically correct, but this gives us with the poor solution, a unsatisfactory solution, because you are getting a smaller view of the line. Similarly, if I had drawn my AVP over here at an angle of 45, then I needed to draw the projector lines through D and E perpendicular to this particular plane, that is my AVP, and then I needed to draw these distances, that is for D the positive distance will be 40, for E the positive distance, that is above HP distance, would have been 5. So this is 40 mm, this is 5 millimeter, and if I join both of these points D2 dash with E2 dash, now this is my auxiliary elevation which I would have obtained. And please see, this elevation compared to this auxiliary elevation stands nowhere. This is a poor solution. So we do not recommend those orientations of the AIP or the AVP which provide us with a shorter solution, which provides us with the shorter view of the lines. So we are now going to omit, even though this is also technically correct, but it is not appropriate. It gives us the reduced view of the line as compared to this view. Similarly, this view is less than 33% of the original view which was obtained using AIP into this orientation. Now I am going to rub out this plane. This is undesirable. I am going to rub off this solution as well. This is again undesirable. So this is my desirable solution to obtain the auxiliary view of an oblique line. So our view should be as large as possible over here. So thank you very much. So with this, we end the first lecture on the auxiliary planes, so that we are now going to pick up the further applications of the auxiliary planes up during the next few lectures. So thanks a lot. Thank you very much.